All right, so one more example. We've got a function h defined using this rule here. So h of x is the fraction with numerator x squared plus 6x plus 8 and denominator x minus 3. So, okay, one of the things you notice right away with this function is that 3 is not in its domain, right? Because if you were to plug in 3 here, h of 3, if you try to write that down, it won't work. Because if you plug in x equals 3, you'll get 0 for the denominator, which is not allowed, of course, right? So what you find is the domain is going to look like this. It's going to be the set of all real numbers except 3. We'll talk more about this particular type of function. This is called a rational function, by the way. We'll talk more about these in the next section. But for now, let's just make the observation that, okay, when the denominator is 0, this function is undefined, so the domain is everything except the real number 3. So if I wanted to write it in interval notation, I could say the domain of h is the union of the interval from negative infinity to 3 along with 3 to infinity. So, and I'll come back to that. Notice we weren't asked for the domain, right? So why did I say this? Well, we'll come back to that. So what were we asked for? We're asked for the x and y intercepts, right? So let's do the usual thing. We'll start with the x-intercepts. And remember, to find the x-intercepts of a function, you want to solve the equation, well, set the function equal to 0. So in our case, it's h. So you want to find h of x. Find out where h of x is equal to 0. So when is h of x equal to 0? H of x is a let's write out one more step. Let's write out the definition of h of x. You got x squared plus 6x plus 8 all over, there we go, all over x minus 3 is equal to 0. Okay, well, what do you do here? Well, what you'll typically see people do is you'll see this. People will just jump to this next step. And they'll say x squared plus 6x plus 8 is equal to 0. And it looks like I've just thrown away the denominator, right? I'm just looking for where the numerator is equal to 0 now. And the reason for that is, well, when is a fraction 0? A fraction is going to be 0 when the numerator is equal to 0, right? That's the only time. So if you want to know when a fraction is equal to 0, which is really what's happening here, our fraction is very complicated, but the left-hand side of this equation is still a fraction. So if you want to know when it's equal to 0, just set its numerator equal to 0. Okay, so, okay, well then now we've got a quadratic. We can factor it. You can check that this factors, right? Look for two numbers that add to 6 and multiply to 8, and you can do the factoring process I showed you earlier, and you're going to end up with this. You'll have x plus 2 times x plus 4 is equal to 0, and that gives you two solutions, right? X is equal to negative 2 or negative 4. Okay, so those are the x-intercepts. And I want to draw your attention to something, and this is why I want to take a moment to make some observations about the domain over here. The two x-intercepts that we got are negative 2 and negative 4. Those came from solving this equation, right? But you could, from time to time, you may run into the situation where you solve this equation and you get some solutions that aren't actually in the domain of the original function. Like, for example, 3, right? 3 is not in the domain of h. So what would we have done if 3 showed up as a solution here? Nope, no problem. Just throw it away, right? Just make that observation. That's why it's helpful. Always acknowledge the domain, even if you don't have to write it out every time like we did here. But just make an observation. Say, hey, I know, make a note of what the domain is, right? Here, in this case, the domain of h is every real number except the number 3. And then that way, when you go to find your x-intercepts, if that number happens to show up, just ignore it and throw it away and don't include it as an x-intercept. Okay, then y-intercept. To find that, remember, we're just going to plug in 0. So h of 0 is going to give us 0 squared plus 6 times 0 plus 8. It's always fun plugging in 0 because everything disappears. You're just going to end up with 8 divided by negative 3, or most people would write this as negative 8 divided by 3 instead. And leave that as a fraction. Leave it exact because that's, or leave it as an exact value because it's always better. So our y-intercept is given by y is equal to negative 8 over 3. And there you have it. Okay, a couple more comments. You can see here I've listed 4 different ways that you can define a function, right? There's other ways as well, but most of the time these are going to be the 4 ways that methods that you use to define a function, and they're going to be the 4 ways that the textbook or my notes use to define a function that you'll encounter. So let's just go through these. One way is just to define a function in words, right? So what that would look like in this example, and actually this one's a bit much, so let's go back to this one. Defining a function in words would, if you look at part A from the previous page, that would sound something like this. F is the function that takes an input value, a real number as an input value, then it multiplies it by 3, and then it subtracts the number 6. And then whatever the result of that calculation is, it gives it back to you. That is what it means to define. That's an example of what it means to define a function in words. Notice it's very clear and very absolute and very precise, and it's a good exercise to practice explaining your functions out loud like that, but it's a bit much to listen to. Like if and especially if the example got more complicated. Imagine doing that for this one. It would take quite a long-winded explanation. And for someone just listening, if they didn't have it written down in front of them, it would be difficult for them to possibly, might be difficult for them to really understand what you're saying without actually writing it out carefully as you say it. So that's one of the drawbacks to a verbal definition. But the benefit of a verbal definition is it really forces you to come face to face with the actual rule that the function is made up of, because that's what a function is, right? It's a rule. So verbally means you explain the rule. Okay, so numerically, that's another method. Well, we've done a couple of examples of looking at functions and writing down table of values for them. Well, imagine if that's all you had was the table of values and you didn't actually have a formula for the function, or you didn't understand the rule. All you had was a table of values to work with. And if that's the case, then that's all you have to work with. One of the advantages to working with tables of values is that they're explicit and there's no ambiguity, there's no confusion that could arise. If you want to know what an output value is for a given input value, just look up the input value on the table and it will tell you, right? And that sounds good because we've encountered tables of values that we drew and they only had like 5 rows usually. Maybe you'll want to do a few more sometimes, but in general it's going to be a pretty manageable number of rows. But in reality, in practice, in the real world, if you look at a function that's defined by a table of values, we're talking tables that are huge, like 100, 1,000, 10,000 rows. That'll happen no problem with a function. So, and in that case, you're not going to be able to even work with those tables by hand. You're going to need to use software to interpret them, right? And you're going to need to be able to search for certain values. You're going to need to use a computer for that. So the disadvantages to numerical tables to define functions is they can be quite laborious to work through. And it's sometimes it might be difficult to tell if a given number is even in the domain of a function. Because think about it, how would you determine if a number is in the function's domain? You'd have to look through the entire table and see if it shows up as an input value, and then and only then can you say for sure that that number is in the domain. And then if you look through the entire table and don't find it, well, okay, then you know it's not, that number is not in the domain. But you just had to look through the whole table to do that, so it can be quite cumbersome. Okay, algebraically, this is quite often the best of every world, right? Or the best compromise, right? Algebraically, this is like the examples we just looked at. So this is an algebraic definition of a function. Whenever you get a formula like this, right? Sometimes they can be complicated to work with because you have to follow the rules of algebra. But the nice thing is, if they're quick to write down, right? And then if anyone who knows how to read the mathematical notation, they can figure out the corresponding output value of any input value that they ever may want to plug into the function. You don't have to tell them a big long list of values or tell them a whole table or explain to them a complicated rule. You can just write this function down, pass it to them on a slip of paper, and away they go, and they can use it for whatever they need. So they're much algebraically communicating functions is quite nice because it's concise, easy to communicate, easy to explain, I mean. But then the person that's using it needs to know how to work with an algebraic formula. Right? Graphically, we've already looked at a couple examples where we had the definition of a function and then we came up with its graph. But you could, of course, as we saw with this first example on the previous page, if all you have is the graph, like we did here, right? We didn't have anything except the graph. You can use the graph as a way to define the function. So maybe that's how you want to explain a function to somebody, just draw the graph and pass it on to them. And graphs are very useful whenever you need to know something about the trend, right? Like this one, for example. You know that, well, -2 is kind of where the function hits its lowest value. But then as the x values move in this direction, what happens to the y values? They seem to increase, right? And then, but as the x values move in this direction, the x values also, or pardon me, as the x values move in this direction, the y values also increase, and that might be useful information for someone to have. And if you have the graph available for them, then you can actually describe those features to them. So whenever you're trying to know something about the trend or the shape of a function, a graphical explanation will be quite useful. Okay, so with those ideas in mind, this example is something I'm going to leave to you. Okay, I'd like you to spend some time thinking about this. Okay, so you've got 4 examples of functions, and they're all described in words, right? But I'd like you to think about if you were somebody who needed to work with these functions, which of the above forms, well, particularly these 3, since they're already given as verbal rules. So which of these 3 forms would you most like to see the function expressed? Which do you think would be the most useful in each of those 4 given contexts? Okay, so I'll leave those to you to think about. That's the end of this section. We'll move on to looking at special types of functions in the next section, section 2.2.